1. So there are 3 files on Blackboard. Introduction to Hypothesis Testing 1, 2, and 3. I'm going to open the first one. Okay, we worked through the first 3 problems here. We worked on during a previous session. Okay, so let's take a look at the 4th problem there. Okay. Example: a student says the average salary of graduates in your major is $40,000 per year. You don't think this is correct. You think that the average salary is higher than this. To show your fellow student is wrong, you simply take a simple random sample of 100 graduates from the past 5 years. This is point and interval, population parameters exercise part 1. Okay, you take a sample. Take a sample. Simple sample of 100 graduates who have graduated in the past 5 years and ask for their starting salary. You find that the sample mean is 35,000 and the sample standard deviation is 4,000. Is there evidence to support your claim that the population mean starting salary is greater than 40,000, right? Because you're comparing it to 40,000. Is different. I'm going to say different. Why is it important I say different instead of greater? Because if I said greater than, now I'm talking about a one-sided test, right? So I just want to know if it's different. Somebody told you that the starting salary is $40,000 per year for 100 college graduates. You take a sample of 100 graduates. Turns out that the mean of your sample, your 100 graduates that you tested, is 31,000. And the sample standard deviation is 4,000. Okay, in other words, your sample, your 100 students, calculate the mean and standard deviation, mean 31,000, standard deviation of 4,000. Well, it sounds like the guy overestimated, they're overselling the starting salary, right? It's really lower than 40,000. But you don't know if it's higher or lower than 40,000. So you're just going to do a single sample. You're going to do a single sample t-test, but it's going to be two-sided. You're not going to prejudge whether or not it's greater than or equal to 40,000. You just want to know if it's different for starters. Okay, so what would my null hypothesis here be? Null hypothesis is that the mean starting salary mu start is equal to 40,000. And our alternative hypothesis is going to be that the mean starting salary is not equal to 40,000. I'm sorry, say that again. Mu. I only have my keyboard. I only have mu available right now. But mu. Anytime I use u, it's probably because I'm short circuiting mu. Okay, so my null hypothesis is that that he's right, that it's true, it's 40,000. My alternative hypothesis is that it's not 40,000. So now how am I going to prove that? Well, I take a sample. What was my sample size? My sample size equal to 100. And I know sigma, right? I was given sigma, so I don't have to calculate it from my, oh no, I don't know sigma. I know the standard deviation for my sample is equal to 4,000. On the other hand, though, it is a pretty big sample, isn't it? Right? Isn't that a big sample? 100. I'm going to assume it's a big sample. So even though I don't know my population standard deviation, I'm going to use Z for this statistic. Okay, so now the test statistic Z is going to summarize that information, right? But before I do that, I'm also going to choose what my alpha is, what my acceptable level of error is. Okay, anybody want to propose what that might be? How about 5%? 0.5, right? So we want the probability that we're going to be wrong if we reject the null hypothesis to be less than 5%, 0.05. Okay, so let's calculate our z-score. Z is equal to x bar, right? X bar in this case is the salary, minus mu, right, which is 40,000, divided by the standard deviation over the square root of the sample size. Okay, I'm going to throw a couple of things in parentheses here so we can follow how it's calculated. X bar minus mu, whoops, over the standard deviation of the sample, because I don't know the population standard deviation, over the square root of the sample size. Okay, that's another way of saying the standard error. So what is Z equal to? Z is equal to, what's the difference between X bar and mu? What was X bar? Okay, I'll put it up here. X bar is equal to, what was it again? 31,000, was it? 31,000. Okay, so what's the difference between X bar and mu? It's going to be 31,000 minus 40,000, so it's going to be minus 9,000. Right? X bar is, I'll spell it out. 31,000 minus the population. What he proposed was the set number that he said it was 40,000 divided by the standard error, and the standard error is going to be equal to the standard deviation 4,000 divided by the square root of the sample size, which is 100. Square root of it is 10 divided by 10. Oops. Okay, so Z is going to be equal to minus 9,000 divided by 400. Okay, well, that's going to be quite a large Z-score, right? Okay, I'm going to change this a bit just so we get it back into the realm of the possible. I'm going to say that our starting salary 31,000. I'm going to make this 32,000. Whoops. 32,000. 32,000. Yeah, it's going to be more than 800. Okay, so it's more than 800. It's 1,000, right? Negative 1,000. Right? So our z-score is going to be equal to. It's going to be equal to negative 2.5. Right? 1,000 divided by 400 is 2.5. Right? Negative 2.5. Okay, so now if I were to sketch this out, I would want to know how likely is it for me to get a z-score, a difference between these two means that's bigger, a larger negative number than 2.5. Well, if I go to my z-table, and I look up the z-score negative 2.50, it's 0.006. So in other words, if I'm so far away from if the two means are so far distant from one another that I'm all the way down here, then that area over here is only 0.6%, right? So the probability of getting that extreme a difference is going to be 0.006 or less. That's how likely that is to occur, right? So now should I use is my p-score 0.006? Am I done finding my p-score? Remember, we started out, we weren't going to prejudge whether it was going to be lower or higher. So in that case, since this came out to be 0.006, I'm going to include the probability that I would have gotten a z-score of plus 2.5. So it's 0.006 here and 0.006 here. So I'm just going to double that and call it 0.012. In other words, 1.2%, right, from the z-table. So what am I saying there? 1.2%. So in other words, the p-value, the probability that we would get that extreme a value if they came from the same population is going to be equal to 0.012 or 1.2%. Okay, now what was my original landmark for what level of certainty did I want? 5%. I wanted to be able to reject the null hypothesis only if there were 5% chance of being wrong. What probability do I actually have based on this analysis of being wrong? Only 1.2%. So can I reject my null hypothesis? Yeah, I can, because my p-value, my probability of being wrong is 1.2%, is less than the level of uncertainty I'm willing to accept, 5%, right? I only got 1% chance of being wrong. I was willing to accept up to 5% chance of being wrong. So my p-value is less than alpha, so I can reject my null hypothesis. And I can say he's wrong. There is a difference that the average salary is not 32,000, it's a different number. So I reject my null hypothesis. And once I reject my null hypothesis, what's the next thing I can say? I can say I accept my alternative hypothesis. Right? What does that mean? I reject the idea of the null hypothesis that the starting salary is 32,000, and I accept the alternative hypothesis that it's not equal to 32,000. It's something different than 32,000. Okay? This is typically the way that you're going to work through a single sample t-test. Right? I mean, each one of these steps we just took pretty much is going to universally apply to single sample t-tests. Okay, I'm going to go to the next document that I have here. Okay, and then we'll take a break. Hypothesis testing. There's another one, Introduction to Hypothesis Testing, Part 2. Okay, I'm going to go through the same exercise now. The SAT score for a population of first-year Hunter students is 620. The standard deviation of scores for this population is known to be 95. What do we know here? We know the population mean is mu. Mu is 620. The standard deviation is known to be 95. This is an example that we worked out before. We're just looking at the confidence interval before. Now we're going to set this up as a hypothesis test. An investigator believes that the SAT score of first-year psychology majors is significantly different, didn't say higher or lower, significantly different than the mean score of the general population, of the entire population. He takes a sample of 36 randomly selected first-year psych students and finds that their score is 648. Okay, so let's state our null and alternative hypothesis. So our null hypothesis is what? It's that the SAT score, the mean SAT score for psych majors is equal to the mean SAT score for all majors. Okay, and my alternative hypothesis, right, is going to be the mean for psych majors, mean score for psych majors, is not equal to the mean for all majors. Notice I'm using mu here because the hypothesis always talks about the population parameter, not the actual sample itself. Okay, so let's talk about the other things that we know here. We know that the X bar, our sample, we took a sample of psych, X bar for psych students is 648. We know that the sample size was 36. Okay? We also know that mu for the general population is equal to 648. Is equal to 620. right? That's known. We were told that. And sigma for the general population is equal to 95. Okay, we're going to assume for the purposes of this study that that there's no difference in the variability between psych majors. So we're going to assume we know the sigma for psych majors as well as 95. Okay, so we know this is what we know so far, right? So now we want to determine if 648 is different enough from 620 to say that they're different with a certain level of certainty. Now let's define that level of certainty. Well, how are we going to define that? We're going to call it alpha. Alpha is equal to, and again, 0.05. Okay, so let's say our null hypothesis is a two-sided null hypothesis. Could be higher, could be lower. We're not going to predict which right now. Okay, so what do we do now? Now we have to calculate how many z-scores apart that these two means are. Our sample mean and the population that we already know the mean of. How far apart are they in terms of standard errors or standard deviations? Okay, so we could take this in a couple of steps. We need to calculate standard errors and then the z-score. Okay, or we could do it in one fell swoop here. Let's do it in one fell swoop. Z, and I'm using z because I know what? Sigma. Okay, z is equal to, it's equal to the difference between x bar for these psych students minus and the mean for all students divided by the standard error. The standard error is really the standard sigma over the square root of the sample size. Square root of n. Okay, let's work that out. Z is equal to, what is x bar again? X bar was 648 minus 620, right? Divided by the standard error. And the standard error is going to be sigma, which was 95, divided by the square root of the sample size. Sample size was 36, so it's going to be divided by 6. Okay, so let's see. How far apart were the two means? The two means were 28 apart, 28 points apart, divided by, what's the standard error here? Divided by 95 over 6. Let's see what that is. 95 divided by 6 is 15.83. 15.83. Okay, so, and the z-score is going to be equal to, it's going to be equal to 28 divided by 15.8323 is going to be 1. I'm going to call it 1.77. Is equal to 1.77. Okay, now those of you that know your normal distribution table, your z-scores, what's the probability of getting two means, if they're from the same population, getting the two means that are 1.77 standard deviations apart? Is it more than 5% likely or less than 5% likely? Well, it's going to be more than 5% likely because we want it to be less. We want it to be further apart, right? So it's more than 5%. So there's more than a 5% chance I could be wrong. What do I want that number to be, that z-score to be? I want it to be, I want the p-score to be less than 5%. What do I want that z? Actually, since we're working with the z-table, if I want an alpha of 5%, what do you want that z-score to be at least or greater than? 1.96, right? The number that would represent two standard deviations apart or 95% confidence, right? So let's look up what that number is. So 1.77, 1.77, 1.7, 1.70, 1, 2, 3, 4, 5, 6, 7 is 0.9616. Well, you know why I got that such a big number? Because it always gives me the area to the left. It doesn't give me the area in the tail. So I would have to subtract 0.9616 from 1, and it comes out to 0.0384, 0.84%, right? Now 3.84%, that's less than 5%, right? But that's not what my p-score is, right? Because now I have to double that number to account for the other tail, right? That only gives me one tail. I have to double that number. So it really comes out to 6.28%, 0.0628. I could have skipped a step there, because since I know that they're symmetrical, I could have just looked up negative 1.77, negative 0, 1, 2, 3, 4, 5, 6, 7, and gotten that 3.84 over there. Okay, I double that number to get what I need. Was that 7? Did I get that right? 3.84, 0.384. So my p-value is equal to 2 times, because it's a two-sided test, 0.0384, and that's equal to, it's actually equal to 7.07, 30, that's going to be.
Hold on.
Yes, what did I do wrong?
When you take away 9.69,
Did I get a different answer? Hang on a second.
When you take away 1 from
1.77.
Right, to the z-score.
Hang on a second.
Was 0.961.
1, 7, 0, 1, 2, 3, 4, 5, 6, 7. Yeah, this is 3.84. Right? Did I pick out the wrong one there before?
So when you saw
3.84. Right. I took away 1.9616 from 1. Right. So that was 3.84%, 0.0384, which is the same amount if I had gone negative 1.77. It just gives me the,
so
I could have.
0.0384, you multiply by 2 to get the p-value.
Because we want both tails, right? Two tails. So we double that, and it gives us 0.07816, that's 76, 0.768, right? So is that greater or less than 5%? It's greater than 5%. So there's a more than 5% chance I'll be wrong if I reject the null hypothesis. So what do I say about this now? What's my conclusion? Do I say I reject the null hypothesis? No. What do I say? I say I fail to reject. Okay? Hypothesis. And what do you say about your alternative hypothesis? Do you say you accept it? You don't say you accept it because you don't know anything about it. You don't know if it's true or not. You only know that you failed to reject your null hypothesis. So your conclusion is always going to be either you reject the null hypothesis and accept the alternative, or you fail to reject the null hypothesis. End the story. Okay. So you see what happened there? We calculated how likely it is that you would get that big a difference in the two means. Okay, we got a z-score or a t-score based on that, and then we found the probability that you would get that big a difference in z-scores or standard errors apart. And if the probability you get that big a difference is less than 5% if they were from the same population, that allows you to reject the null hypothesis. The p represents the probability that you would get that big a difference if the two means were the same, were really the same. In other words, you'd be wrong if you reject the null hypothesis. I'm sorry, minus the minus 1 only because if I want to figure out what area is left in the tail for plus 1.77, right? Well, this table gives me the area from here to the left. It doesn't give me the area in the tail, right? So this area turned out to be, say, 96%, right? So that's the area to the left is 96%. So the area that's in the tail is only 4%. So that's why I use the 1 minus the 96%. It's because I'm looking for the area that it's not giving me, what's left. the difference. So like on this side, for instance, if I were looking on this side, if I'm interested in the area in the tail, it's going to give me the area in the tail. I don't have to subtract it from 1. But if I'm looking on this side, it's giving me the area to the left, not the area that I want over here.
But so I always get confused of knowing which side it falls on.
Well, it depends on the tail is the part you're looking for. But on this table, right? Remember, this is the positive side. This is the negative side, right? These are all negative z-scores. This is
So the
positive
negative
z-scores.
side you don't subtract.
Well, if you only want the tail, you don't subtract because it's going to give you what's in the tail. It gives you the percentage that's left in the probability or the area of the distribution. It gives you that area that's in the tail to the left of the z-score. When you're on this side, if you're interested in what's in the upper tail, right, then in order to know what's in the upper tail, you have to subtract the number it gives you because it doesn't give you this area. It gives you the area from that point down. Right? Okay, tell you what. I've been joining on here for about an hour and a half now, right? More than that, God, more than that. Let's take a break, okay? And take a break, clear our minds, then we'll come back and we'll attack this again, okay? And we're going to use we're going to start to use SPSS to solve these problems, which you're going to love because it takes a lot of the work away. Yes.
Just a question.
Yes.
So if it's always above 0.05, are you gonna reject? Fail
No,
to
it's going to be based on what you define your alpha as. In other words, if I said I'm willing to accept 10% chance of being wrong,
If it's always above the alpha,
you
you're
fail
gonna
to reject.
you fail to reject.
Right.
Okay.
Right, because it's
Alright,
more
so it's
likely
always-
it's more
okay.
likely you'd be wrong than the level of risk you want to take.
Okay.
Alpha represents 5% chance of being wrong
Yeah.
or 1% chance of being wrong.
Yeah.
So you want the p-value to be less than that number because the p-value represents your real chance of being wrong.
Okay. Okay.
Okay, good. Let me run outside quickly.
Oh, it depends how certain you
Because I picked like decreased obesity.
Yeah.
It's, I don't know, it's just it's tricky, and she grades so tough that
Yeah, I know. I feel like I'm doing well in the class, but I just feel like I should be doing better. I'm like, yeah, she's, you know,
like what'd you get on that last
37, I think. Like I just barely, got my hang of it. And so I keep wanting, I don't want to seem defensive and argue my grade, but then again, I want to, go, hey, this was like this most recent one. The first one, there wasn't enough space, so I had to like decide what I was going to take out, and then there was like a disconnect and something. She was like, I don't, why did you pick this? And I was like, I guess it's not clear that it's, felt more relieved to the end than the beginning. Anyway, and then because I still had budget left, and I was like, oh, I'm gonna be fine, And then, but that wasn't clear my thing on the first one. And then this most recent one, I said, because I've done stakeholder interviews for my job. This was actually a breeze. I had no challenge. I guess I didn't specifically say I had no challenges, but I said this was a breeze. It was so refreshing to be able to offer something to a stakeholder that I was interviewing, rather than having to, asking so that I could, help this other company turn profit. And so, I guess I didn't specifically say I had no challenges, but so it was actually Sandra who said, what about challenges or reflections? But I'd said this was,
I didn't have any.
yeah. So anyway, it's one of those things.
Yeah, it's definitely
Yeah. Anyway, no. Yeah. the hardest part is the junction. Which step is something that helps me think about it.
Yeah.
I have to like.
See, like I had like my formatting is so bad. But it's like 12.5.
Yeah. Okay, so you only
But
did
now, here it is.
good.
So now,
Yeah, I asked her during she said it's hard to have
no,
like
because I was, about,
significant.
Yeah, I don't even know.
Yeah.
Probably not. That's like
They're gonna find the stuff that you forgot.
Oh, so
Yeah.
oh, yeah. On the overall. Yeah, so I'm gonna do.
Probably gonna take off the formatting because my one box is not on the bubble.
So.
Yeah, wait, so she was okay with that? When I told her about gluten free, she said,
I tried to bring it up.
one thing with that.
Well, she told me,
You
she said, so I was like, oh,
or make it a little wider so
also,
that.
yeah, she was like, I was like, oh.
Did you sign it already?
I know, you're so tired of looking at it, right?
No, but I finished
I was like, tomorrow. Yeah, it was like, when I do like your overall, it was like, yeah, what happens. And then she was like confused by my question. So she's like, oh, I'm like, I'm a little confused. Like your question, but she was like, you can either, because she's like, the component of the diet, you know, like health supplement, she's like, always doing. So she's like, or the component of the diet.
I would rather have a job
She
where
wants to do one component of the diet, or the overall
Oh,
diet.
so you're doing, you're still connecting to health outcomes?
Yes.
With the whole diet?
Yes.
That's what I'm doing, yeah, for gluten free.
in New York City.
I mean, gluten free is my
Yeah,
favorite,
she
really.
was like,
And you can't
yeah, so she
say,
was like, oh,
can't
I
make
was
your
like,
schedule
so,
so
you
that
know,
you
she was like, okay, either.
Oh, that's your
It's
choice.
not
Yeah,
but you said she's not.
Not.
I didn't want to do that, and
I find it
because I
important.
wanted to get my insurance, so I didn't have to pay for the
Yeah.
hospital. But
I beg you.
I might change it to
So
like
I'm doing like.
Because for teaching it.
weight loss.
I don't even know.
Especially with next semester, like
Please.
So,
Please. I would not
classes
recommend
started
that.
next semester.
It's a
I
crazy.
don't want to be able to like 30 minutes.
So,
Sometimes my friend makes me
I
up.
just wasted.
Yeah.
It's not terrible.
Yeah.
My life.
And 11:30 the trains are slower.
One
Sometimes
big
I don't
issue
fire
in my head.
Yeah.
It's like, oh, your nursing life? My registration. Your registration.
Where you gonna go for? So I can talk about
3 months. 3 years.
Yeah, because there's no way you would
Why you even
do the diet.
You could do it on
Wow.
the
Doesn't make
computer.
sense.
I did it already. I got it. So I'm
Right, 'cause
supposed to
you're not
take it
really
tomorrow.
Yeah.
So my everything is all in place in my head. And it's tomorrow's the deadline. What's the big
So you
deal?
told you got it, right?
I have it. It came over the weekend. I did it last Friday. Gosh, it's a big deal.
Because they cannot let you work if you don't have a license. They'll get it to know what's the big deal. You crazy. I don't know. I never understood. Remember they say all of their books and stuff.
The fact
And they
that
don't
they
have to.
are.
I guess they look at their books. You cannot work without a license. You can't work anywhere without a license. With what they are.
Places in both of them
But
states.
either way,
They're like a root. You got it last Friday. Every week you get it. So she just passed me a copy or whatever.
I was checking out and like my total was
Hi,
like.
good birthday. Listen, why so early now at work? If I got the stuff for you, I was
And then
going
like,
to
like,
So basically, when you punch in orange.
Yeah, remember.
Very.
Sure what? Sure what?
Yeah, I think it's
Oh, because remember last Friday I applied for it? And it went to my mother-in-law's house. So it came on Friday, and my husband brought it over.
Yeah, literally.
I'm like in love with potatoes.
I'm 25% Irish. I'm not even Irish. I love that.
What's the name of the woman again, the Indian woman of the You know?
I don't know, but if you look at it.
Tomorrow morning, 8 o'clock, I'm in the
No, I really found out it's too much bad.
I feel like I don't know why I was doing this. Like, I was gonna take this out for a couple questions, like, because I knew this had a symbol on it, but I was gonna take it out. I want to have a pod diet. I want to do it.
Yeah, if you could send that.
And also, it's all issues, like, I know, but obviously you're gonna have some health issues.
It's special nurse.
But that's not like saying, like,
I could give you opposition, right?
It's mac and cheese all the time. Right. Because there's like a disconnect between the research and what how people follow it all. It's like research is like it seems like there's like because they're able to like because they're eating well, but like a lot of people
Oh. I got some stuff like that. I'm gonna take it.
Right. Do it that way.
And same with gluten-free, like,
Deal.
on the study
One
about
of my classmates here, like, to be
when
sure.
gluten-free diet and
And she's looking at me all kinds of way.
wait, what?
She said, "Oh, you can
Oh,
work
yeah.
anywhere with all that."
Oh, good.
Body like.
No, so now the study.
No, she's telling me I have to get it.
Gluten-free does promote weight loss, and I'm looking
She's
at
gonna get it, whatever. It's always
health
good.
crutches, like female, that like worked out.
So the
and
majority,
stuff.
have you found the majority of the
I have to do more research, but a lot. The thing with women, which I'll say, is that
I
a
was
lot of
looking
research
at
is
this
on
today is not
women who have celiac. Because that's what the diet is prescribed for, so it's a little bit limited, like there still needs to be more research on people who go on a gluten-free diet that don't necessarily need it. So, I mean, it's just like, yeah,
But of course, but I mean, it is prescribed to people. I know.
right, because they literally can't have gluten, like it destroys their intestines.
So we're like, if you're doing it,
I just decide to ignore your parents.
Yeah.
Yeah,
It's messed up, and like they
You know,
then they can't.
you know, the
It's so interesting, because like my boyfriend is like celiac, but he has dermatitis type 1, and he eats like anything with gluten, it'll like skin rash. So he's like, I guess you can call it like an intolerance. Or like an allergy. Yeah, they have like it is called like non-celiac. Yeah. Yeah.
Also, I mean, I got like really, like,
Anyway, this guy's back.
They still have to do more research on that too.
All right, I'll talk to you later. Okay, bye.
Yes.
You said our conclusion was rejecting null hypothesis. But what about the alternate?
We failed, no, if we fail to reject it,
The first example.
the first example, if we reject the null hypothesis, we accept the alternative. In other words, if we can say that we can reject the idea that they're the same, then we can say that we accept the fact that they're different.
And the second one, you failed to reject the null hypothesis.
That's we're done. You can't say that the alternative is true because that's not what you were trying to prove.
Or if you're trying to prove the null hypothesis.
That they were different.
So reject the null and accept the alternative.
Right.
And what's the next one?
If you fail the null, then
Fail to reject the null
yeah,
hypothesis.
then that says you don't go any further.
Right. If you fail to reject it,
You fail to reject it.
in other words, you can't say that they're not different. They're not the same. So you're not going to make any comment about whether
So
or
you
not they're
fail
different.
when it is less than.
When P is, you reject the null hypothesis when P is less than alpha.
When P is
Less than alpha,
less than
you
alpha.
reject the null hypothesis.
And for the rejection, the reject what would be what?
That's when you reject it, if P is less than alpha. If P is not less than alpha, then you fail to reject the null hypothesis.
this year's.
Yeah, no.
Okay, we're going to try another example right now. Okay, I'll tell you what, let's try number 2 together.
Yes.
I'm going to read it. The mean number of close friends for the population of people living in New York is 5.7. This, in other words, that's known. It says population. Mean number of close friends, if you surveyed everybody in New York, it's 5.7. The standard deviation in this population is known to be 1.3. So we know mu for the general population in New York, and we know sigma for the general population. An investigator predicts that the mean number of close friends for introverts will be significantly different from the mean of the population. Now I'm guessing he thinks it's going to be less, but he didn't say that. He just says different, right? So that sets us up for a two-sided hypothesis, not a one-sided. The mean number of close friends for introverts for a sample of 26 introverts is 6.5. It turns out to be more. Does this data support the investigators' prediction that it's different for introverts than it is for the rest of the population? Okay, so testing the claim above, use a 95% confidence interval, single sample hypothesis test. In other words, only one sample, the other one we know the population. State the null and alternative hypothesis. So I'll wait for you guys to write that down. I'm going to do it step by step with you. And I'm going to wait for you guys to write down your own null and alternative hypothesis. In the meantime, I'm going to just put in some of the facts of the case here. Mu is equal to 5.7. Mu for New York, for all New Yorkers, 5.7. Sigma equals 1.3. And for our introverts, mu for introverts is equal to, oh, excuse me, not mu, I don't know mu, I know X bar. For introverts is equal to 6.5. And my sample size is equal to 26. So I'll wait for you guys to, you don't need that for your null and alternative hypothesis. When I see people stop writing, I'll give my own try at that. Okay, so I'm going to give my own try at this. Okay, my null hypothesis is that there's no difference between the two. In other words, that mu for the entire population, all, is equal to mu for these introverts. And my alternative hypothesis is mu for the entire population is not equal to the mean for all introverts. Now, I don't know what mu is for introverts. I know what mu is for the entire population. Okay. Yes? The mean of the population of all people. Significantly different than the mean of population. In other words, significantly different than 5.7. Than 5.7. For the introverts, is going to be more than 5. Is going to be different than 5.7. In other words, the mean for all New Yorkers is 5.7, which sigma is equal to 1.3. But he takes a sample and he finds that the mean for introverts is different. It's 6.5. Right? Maybe introverts have very few non-close friends, but just close friends, and they have more. Who knows what's going on there? We're only interested in seeing if it's different. So I could do it this way. I could write the mean for introverts is equal to the mean for all New Yorkers. Mean for introverts is not equal to the mean for all New Yorkers. Right? But I didn't change anything. I just turned them around. I just reversed them, right? Okay, another way for me to say this, another way I could phrase this is that the mean for introverts is equal to the mean for all New Yorkers, which was equal to 5.7. And the mean for introverts is not equal to, as the alternative hypothesis, not equal to, not equal to 5.7. See, those two things are the same thing, right? Because I know what the mean for all New Yorkers is. That was given to me for the population of all New Yorkers. Everybody comfortable with that? I could phrase it this way, or I could phrase it this way. I'm really saying both. I'm saying the same thing in both. Okay? Anybody uncomfortable with that? Right? So this is it's a two-sided hypothesis because we don't know ahead of time whether the mean for introverts is going to be greater or less than. Now I take my sample. Turns out I sampled 26 introverts, and their mean turns out to be 6.5. Okay, so now I'm going to say calculate the z-score or t-score. I'm going to say z-score because I know what?
So
I know sigma, right? So I can calculate z-score. Yes, go ahead. What are you going to say?
So we're skipping go all the way to the
Well, it's the same thing.
Okay.
You know, because I'm going to calculate z-score. I'm going to do it in one stop. Yeah, actually, why not? Why don't you guys I'm going to undo that then. Okay. Calculate the standard error first, and then we'll calculate the z-score. Okay. Let me get back to where I was. Yeah, calculate the standard error first, and then we'll calculate the z-score. I'll let you calculate standard error, and then I'll do it. Give you a little bit of a hint up there. Okay, so I'm going to go ahead and do this. The standard error is equal to sigma. What was sigma again? Well, we told us 1.3 was given to us was 1.3 divided by the square root of the sample size. The sample size was 26. So I got to calculate that. I got to bring my calculator up. So I'm going to clear. The square root of 26 is 5.09 or 5.1 practically. Okay, I'm going to put that into memory. And let's see, it's 1.3 is sigma, 1.3 divided by the square root of 26 is equal to 0.25. I'm going to call it 0.255, round it off a little bit, is equal to 0.255. Okay, so now I'm going to calculate my z or my t test. Which one am I going to do, c or t? Do I know sigma? Yeah, I did. So I'm going to use z. Z is equal to x bar for my sample, right? Minus mu, the known value for all, right? Divided by the standard error. I calculated that ahead of time. Otherwise, it would have been sigma over the square root of n. Minus the mean for all, right? New Yorkers. So x bar, the result of my mean for my sample, was equal to 6.5 divided by my standard error, which was 0.255. Oh, I'm sorry, 6.5 minus 5.7 divided by my standard error, which was 0.255. Right, so I'm gonna clear that. So it's gonna be 1.2 divided by 0.255. That comes out to 4.7. So Z is equal to 4.7. Okay, so now I'm going to look up on my Z table what p-value is associated with a Z-score of 4.7. Okay, go to my Z table, right? Well, it doesn't even go up that high, does it? Right? Right, so the area in the tail is going to be way less than 1/10 of 1%. I'm going to call it 1/10 of 1%, 0.001, just so I can use it as a placeholder. If I use 0.001, what do I have to do with that 0.001? Because I'm only looking at one tail. I have to double it times 0.001. Okay, so P is equal to 0.002. What was my acceptable level of error again? Alpha is equal to 0.05. So what I'm interested here is P less than alpha? So is the probability of being wrong, if I reject my null hypothesis, in other words, the probability you would get this big a difference in the two values, the two means, is that less than 5%? Yeah, it's 0.002. P is less than alpha, right? Since P is less than alpha, what can I do about my null hypothesis? What did I hear over there? Reject the null hypothesis, right? You can reject your null hypothesis. Reject your null hypothesis. And what can you do with your alternative hypothesis? If we reject the null hypothesis, we say that they're not the same. So therefore, we can accept our alternative hypothesis that they're different. Right? We can accept our alternative hypothesis. Remember, the null hypothesis started that the two were equal. Right? Once we reject that, say that that's wrong, we can accept the alternative that they're different. Right? So we've proved with better than 5% chance, less than 5% chance of being wrong, that there's a difference between the null hypothesis and the alternative hypothesis. In other words, a difference between the two means, the mean for all New Yorkers and the mean for population mean for all New Yorkers and the population mean for introverts. Okay, I'm going to modify this question slightly. I'm going to say that the mean for all, instead of being 5.7, is instead 6.0. Well, what changes here if it's 6.0? Right? Well, I'm sorry. I'm going to leave that 5.7. I'm going to say that our sample came back being 5.9. Is that big enough? Let me think about this. 0.2. Yeah, our sample came back 5.9. Okay, well now if I go through this whole thing again, right? Mu for the introverts 5.7. That's the same, right? Hasn't changed. Just our sample means changed. So our standard error hasn't changed. It's still 1.3 divided by the square root of 26, the sigma over the square root of the sample size. But Z has changed. X bar now, instead of being 6.5, X bar now is 5.9. Right? 5.9 minus 5.7 is 0.2 divided by 0.25. 0.2 divided by 0.255 is 0.78. Right? So my Z value now is 0.78. Okay, what is the p-value is associated with a z-score of 0.78? Well, let's go to our table. If I go to our table, 0.78, 0.0, positive 0.0712345678 is 77.94. I'm going to call that 78%, right? Is 78%. I'm sorry, did I get the wrong one? What was I looking for again?
0.78.
0.78, okay. 0.7101234567 I'm still going to call it 78%. I'm going to round it down, call it 78%. Okay, so just to make things go a little quicker, 78%, right? So what is that 78%? 78% is below that level. That's not the amount that's in the tail, in that upper tail. So 78%, that leaves 22% in the upper tail, right? 100% minus 78% leaves 22% in the upper tail. So that's the probability that I would get a value higher than 5.7. I got to add to it the probability that I get a value lower than 5.7. In other words, double that 22%. 0.22 times 2 for a two-tailed test. 0.22 is 0.44. So I have a 44% chance of being wrong if I reject the null hypothesis. In other words, there's a 44% chance that I could get this extreme a difference, 5.9 to 5.7, if there's really no difference between introverts and all the rest of New Yorkers. So since my chance of being wrong is 44%, and my acceptable chance of being wrong is 5%, what do I do with my null hypothesis? Should know this by now. What do I do with my null hypothesis? I fail to reject it, right? Because I haven't proved it, right? I failed to reject it. What does that tell you about whether or not they're different? It doesn't tell you anything. All it tells you is you can't say that. It doesn't tell you that they're different. It doesn't give you any conclusion about their difference. It just tells you that you can't prove that they're not the same, right? So you can't say that they're not the same, so you can't make any other conclusion about whether or not they're different or not. Okay, so you failed to reject the null hypothesis. Done, end of story. If you reject the null hypothesis, then you can accept the alternative, that if they're not the same, they must be different.
Professor,
Okay, yes,
I need to back it up a little.
yes.
4.7. How you get a 4.7? Z is equal to 4.7.
Well, that was the first time around.
Yes, I was trying
Well,
to
what is the mean for our sample? The mean of the sample, right? The mean number of close friends for a sample of 26 introverts is
Is it 6.5?
6.5. Okay. And what is the mean for all New Yorkers, the mu for all New Yorkers? 5.7. Okay, so if I look at how I calculated my z-score is the mean for the sample minus the mean for all New Yorkers. So that's what was it again?
6.5
Minus 5.7, 6.2, what was it, 6.2 or 6.5?
1.2
6.5 minus 5.7, right,
divided
is
by
1.2, right? Is it?
Mm-hmm.
6.5 minus, no, it isn't.
You said 1.2.
But that's not. 6.5, I'll go back and do that again. 6.5, yeah, 0.8. So that should be, you're right, 0.8. 0.8. Yeah, the math is wrong, but I'll bet you still can reject the null hypothesis.
All right, so 0.8.
How come nobody else noticed that? Is anybody paying attention here? Okay, here, let's try that again. So it's 0.8
No, divided by.
divided by the standard error, which was 0.255. So what's the z-score? The z-score is 3.14. Z-score of 3.14.
Mm-hmm.
Okay, so what's the probability? What's the tail? What's the percentage in the tail for a z-score of 3.14? So I'm going to go to my z-score table. So a z-score of 3.14. 3.10123 is 0.992. So that's 0.0008. That's about 0.01. It's about the same percent. Remember I said rounded off to 0.01 because it was so small. So we wind up getting the same p-value. When we double it, 0.002. Okay, and again, remember, you can always flip this. A positive the area in the tail on the plus end for 3.14 is the same as the area to the left of negative 3.14,
So then it's gonna be 2 times what?
0.0008.
0.0008.
Yep, 2 times what this area is, right? Look up behind me.
That's a negative, right?
No, it's the z-score is negative. The area is always positive. Areas are always positive.
This one is come up negative.
No, I'm just saying that if you don't want to look up 3.1,
3.14.
3.14 is 0.9992. So if you want the area in the tail, you got to subtract that from 1. So it becomes 0.0008, right? But you could instead of looking at this 3.114, right? You could look at negative 3.14. It'll give you area in that end of the tail, which is the same as the area that's in this end of the tail. You don't have to bother subtracting from 1, right? You don't have to bother subtracting from 1 because it's symmetrical. The two tails are going to give you the same area for the same z-score in the tail.
So 2 times 0.0008.
Okay, let's try another one of these. We'll beat this to death if we have to. But I don't want to do that one. Here's a proportion. Let's do a proportion. Okay. The proportion of people attending a Hunter that report having a close friend who's a diligent student is 30%. When I went to college, I didn't go to SUNY New Paltz. The SUNY New Paltz had a reputation when I was in the late 60s of being a party school, right? So it probably still is, right? I'm guessing. At any rate, yes, at any rate, I'm not sure what its reputation is, and I'm interested in knowing if it's still true. An investigator randomly samples students at SUNY New Paltz and finds that 20 out of 100 report having a friend who is a diligent student. Can he confirm that the proportion of workaholics at SUNY New Paltz is different than it is at Hunter? Okay, so at Hunter, we're going to assume that the population proportion of diligent students is 30%. Okay, so we're going to start by saying that P, not P cap, but P for Hunter is equal to 30.0.30%, 30%. Okay, now we're going to go to New Paltz, and we don't know what P is for New Paltz because we're going to do a sample. P cap for New Paltz is equal to what proportion are diligent students up there? 20 out of 100. They sampled 100 students, and they found that 20 out of 100 is 20%, 0.20, right? Are diligent students. Okay, so our sample size is 100. Okay. So now let's state our null and alternative hypothesis. Okay, first of all, for Hunter, we're going to assume that that's a population proportion for Hunter, right? All students. Okay, but for New Paltz, it's going to be a proportion. It's going to be a oh boy, I didn't mean to do that. I want to change the color, but nah, I'll just leave it like that. Okay, let's state our null and alternative hypothesis. Okay, our null hypothesis is that the proportion from our sample, P cap, right? P for null poles, not P cap, but P for new poles, the entire population proportion for new poles is equal to the proportion that we know for Hunter. Okay, and our alternative hypothesis is going to be that P for new poles is not equal to the proportion for Hunter. Okay, and this is going to be our H null. This is going to be H alt, alternative hypothesis. Okay, so if I want, I could set this equal to 0.30 because that's what Hunter is. 0.30, not equal to 0.30. Instead, if I wanted to put that in instead of a P Hunter, I could put 0.30 in instead. Okay, so let's test that. Okay, the first thing I need to do is, since I've stated my known alternative hypothesis, I want to calculate my standard error. What's the variability here? What's my standard error going to be equal to? Okay, remember the standard error for a proportion? I'm gonna type in the formula, and you guys can do the actual calculation. Square root of P times 1 minus P. P over N. Sample size. Square root of that whole thing. If I'm going to do this right, I'm going to put on all these parentheses. Actually, I think that should work. Okay, I'm going to leave it up to you to tell me what that is. Okay, anybody working that out? Okay, what's that going to be? It's going to be equal to 0.3 times 0.7 over 100. And then you're going to find the square root of whatever that is. 0.3 times, what is 1 minus P? If P is 0.3, oh, it's late. We're getting late here. Does anybody in this class keep track of time? Okay, I want to do one more example after this, so don't split on me, okay? Right, we're class over 3:40, right? Yeah, 1 minute ago we class. We got 1 minute. I got 3:39, and I'm the Naval Observatory here. So, okay, so I'm going to do this. I'm going to work on this real quick. 0.3 times 0.7. Whoops. Times 0.7 divided by 100. Divided by 100, sample size is 100, right? Recall that. And we find the square root of that. Whoops. Oh, shit. That came out wrong. 0.3 times 0.7 equals this, divided by 100 equals this. Find the square root of that, and it comes out to about 4.6%, 0.046. Okay, standard error is 0.46. 4.6%. I 0.046. 0.046 or 4.6%.
0.21 divided by 10.
0.21 divided by 100. And then you find the square root of the whole thing.
Oh.
Right? Remember the formula. Remember, look at the formula. Okay, so what is the z-score here? The z-score is, because it's a large sample size, we're going to use z. The z-score is equal to the difference between the probability for Hunter students, probability p cap for new poles, minus mu, minus p for a Hunter. That was a true proportion, divided by the standard error. Or in other words, the z-score is equal to The difference between them is 10%, 0.10, divided by 4 point, what did I say was 0.46? 0.46 is equal to, and let's do that real quick. I'll clear this out. 0.1 divided by 0.046 is equal to a z-score of 2.17. 2.17. And what's the p-value associated with 2.17? I'm going to look up negative 2.17. Negative 2.17, because I know it's going to be the same thing. Negative 2.17, negative 2.10, 1, 2, 3, 4, 5, 6, 7 is 1.5%, 0.015. But I want to make this a two-tail test, so it's 2 times 0.015. We're counting for both ends. That's equal to 0.03, 3%.
No, it could
Look it up again.
A negative, what did I say was the z-score?
2.17.
2.17. 0, 1, 2, 3, 4, 5, 6, 7, 0.15. See it there? Okay, so that's 1.5% doubled is 3% is our p-value. What is our acceptable level of error? Alpha? Is it less than alpha? Is equal to 0.05. Is 0.03 less than 0.05? Yes, it is. So what do we do our null hypothesis? We reject. Yeah, because there's less than 5. There's only a 3% chance of being wrong. That these could be that different and be from the same population, right? So we reject our null hypothesis, and we accept our alternative. Okay, and I'm going to do real quickly, I'm going to take a look at another one of these problems, which is in the other Word file that's on here. Open.
Professor, we would use the T score when we don't know sigma for this type of problem?
Yes.
That's when
Well, not on that one because it's a big sample size.
Okay.
100, right? Proportions, we almost always work with a big sample size. But in general, yes, and we'll get to that. Then we're going to look up the t-values to do that. We'll get to that next week, and we're going to get into next week, we're going to get into 2 sample t-tests when we take 2 samples instead of just 1 sample. Well, it's a natural progression, right? I mean, this is when you only take 1 sample and compare it to a known number. Right. I just want to show you quickly another way of doing this. What's that?
Which exercise are we in?
I'm sorry.
Which exercise?
I'm just about to open one. You don't have to, just look at what I'm going to do. Don't worry about it.
Okay.
This time. Actually, what I'm going to do is I'm going to go to Blackboard, and I'm going to, okay. The desktop save this. Okay, I'm going to open SPSS. Actually, I'm just going to open SPSS. I'll make my own example up. Just to show you quickly how we might work with this in SPSS. I'll throw a few numbers in just so you can see how this works. Okay, so I'm going to look at blood pressures. I'm going to sample 10 people, 90, 89, 90, 89, 78, 99, 78, 90, 89, 88. Okay, there's 10 people. There's the blood pressures. I'm going to go up here and analyze this. I'm going to find the average blood pressure. Okay, descriptives. And I'm going to ask it to calculate the average blood pressure for me. And the average blood pressure here turns out to be, from this sample, the average blood pressure turns out to be 88. Okay, so I'm going to say that I want to compare this to a population that I know the average blood pressure is 91. So I want to know whether the average blood pressure for the population I took this sample is different than the average blood pressure for a population I know to have a mean of 90. So I'm going to do a t-test. I'm going to see how many standard deviations apart these are. So I'm going to go ahead and analyze, and notice that beyond statistics, beyond descriptive statistics, the next thing we're going to work with in SPSS is compare means. And notice how we have a number of these ways to compare means. One is a one sample t-test. The other is an independent, meaning two sample t-test. Another one's a paired sample t-test. One's another thing called analysis of variance, and so on and so forth. We're doing a one sample t-test. We have one sample of 10 people, and we're comparing it to a known mean for another population. So I'm going to click one sample t-test. So one sample t-test, first thing it sees my numerical variable here, my 10 sample of 10 people. That's what I'm going to compare. And then for my test value, I am going to put in the value that I said was the mean for the other population. What did I say, 90 or something like that? 91? I'm going to put in 91. So I want to know whether or not I can say with less than 5% chance of being wrong that these two means are different. Okay, so my null hypothesis is that my mean, the x bar that I have, is equal to the mean that for that other population, 91, or it's not equal to 91. So I'm going to say go ahead and do this calculation. It does a t-test. It says that the difference in z-scores, is 1.55, right? Which means that there is a two-tailed process. It calls the p-value significance. The p-value, the probability that you would get this big a difference if these two were from the same population, is 15.5%. That's my p-value. If my p-value is 15.5%, can I reject my null hypothesis? No, because it's bigger than 5%.